Hey everyone, as a senior solutions architect, I am absolutely thrilled to lead today's explainer. We're going to take a highly analytical approach to chemistry today, really looking at it through the lens of systems engineering. We are going to conceptualize a fundamental chemical concept, a solution, by framing it as a deployed runtime environment, or a container, if you will. All right, let's dive right into this deployment strategy. Here's our sprint backlog for today's technical briefing. We'll be hitting environment architecture, the host and payload, defining the runtime, the aqueous environment, system setup and configuration, and finally, thermal constraints and parameters. Let's get right to it. Section 1, Environment Architecture. Let's establish our system foundations. In chemical engineering, our deployed environment has to maintain absolute structural integrity. A homogeneous mixture is a system where the composition is uniform throughout its entire volume. This basically means that no matter where you sample the environment, top, bottom, or right in the center, the properties and state remain completely identical. It is a perfectly balanced container. Section 2, the host and payload. Let's break down our system dependencies. Any properly deployed solution is going to consist of two distinct components. First, a solvent is the component that exists in the largest amount, acting essentially as our host operating system. Conversely, a solute is the substance which is dissolved in the host environment, functioning exactly like our deployed application or data payload. You simply cannot have a working solution without both the host OS and the payload successfully integrated. Moving on to Section 3, defining the runtime, or our resource concentration. This brings us to a brilliantly simple primary configuration setting, molarity. Molarity, which we denote with a capital M, is defined as the number of moles of solute per liter of solution. Think of this as our resource concentration. But here's the absolutely crucial point. The volume parameter, that capital V, must represent the total volume of the entire solution. That means the host plus the payload, not just the solvent alone. It's the full footprint of your runtime environment. Now, before we actually calculate anything, I need to enforce a strict syntax rule for our verbal communication today. When you see this specific designation on your readouts, it is read aloud as 1.0 molar. We never say 1.0 molarity. Maintaining this professional volumetric integrity is absolutely crucial when you're communicating system specs to the rest of the engineering and math teams. Section 4, the aqueous environment. Let's look at the default host OS. What's really interesting here is the medium itself. Water, which is often called the universal solvent, creates what we formally call an aqueous solution. Just like a standard Linux kernel forms this incredibly reliable base for countless software deployments, water serves as the robust foundational host OS for a huge variety of chemical payloads. This ranges from maintaining precise calcium levels in a swimming pool, like you're seeing here, all the way to running the complex biological functions inside our own bodies. Section 5. System setup and configuration. Time for a live deployment simulation. Okay, here is our specific payload. We are looking at distilled white vinegar, which is a deployed solution of acetic acid acting as the solute in water. For our simulation today, we're going to provision an environment by deploying exactly 35.3 grams of acetic acid into enough water to create a 0.500 liter runtime environment. Let's run the math to determine our molar concentration. Here's our computational algorithm, broken down step by step. Step 1, we convert our payload mass to moles. So, 35.3 grams of acetic acid, divided by its molar mass of roughly 60.05 grams per mole, yields about 0.588 moles of payload. Now, for step 2, we verify the total environment volume, which we've already set at 0.500 liters. Step 3, we execute the molarity function, simply taking moles divided by liters. So, 0.588 moles divided by 0.500 liters resolves to a final molarity configuration of 1.18 molar. Boom, our environment is successfully configured and mathematically sound. Section 6, Thermal Constraints and Parameters. Let's talk system limitations. Before we wrap up, we must perform a rigorous constraint check. You see, the physical volume of liquids isn't perfectly static. Volume naturally expands and contracts with heat. Because our primary molarity metric relies directly on volume as its denominator, molarity is inherently temperature dependent. It acts as a system variable that inherently changes with the thermal state of the environment. If the temperature spikes, the volume expands, and the overall molarity concentration artificially decreases, even though the physical payload, your actual solute, remained exactly the same. This brings us to a fascinating limitation of our current architecture, and I want to leave you with a rather provocative thought. how might a concentration gradient force us to completely reevaluate our host OS configurations under extreme thermal loads? When those environmental parameters start shifting, how do we actually guarantee the stability of our system? Keep that in mind as you review today's architecture specs. Thanks for joining this explainer, and I really look forward to our next technical briefing.